everyone. Welcome to the next lecture on the complex analysis. Today I will explain you the argument principle. Myself Dr. Harish Garg. You can follow and subscribe my YouTube channel where you can find the playlist of the complex analysis. In this playlist you can see the various lectures related to the singularity, maximum modulo principles and many more lectures related to the complex analysis available. You can watch and subscribe my YouTube channel. Now, before I just directly start with the argument principle, firstly, I will give you some motivation and the question which you can think why there is a need of the argument principles. For example, if you consider any of the complex functions f of z and a closed contour C, can you find the value of this integrations f dash divided by f? Can you find this integration? You can choose any of the f. If I choose f is, for example, z square plus 1 raised to power cube divided by z square plus 5z plus 4 raised to power 7. Can you find the integration of this component? Again, you can see it is not possible that you can find the derivative of this function. It is not an easy target for you that you can find the derivative of this function. Fine. Then the question arises is how you can find the value of this integrations. The concept is very simple. There is no need to find the value of the f dash. If you are able to remember what are the zeros and the pole of the given functions. For example, if I consider my function is this part, can you find the zeros of these functions? Can you find the pole of these functions? If yes, then you can evaluate these integrations within a couple of seconds. So for example, if I assume all these blue colored dots are my number of the zeros or the zeros of the function f, and these red colored dots are my number of the poles or the pole of the given function f. So can you calculate the total number of the zeros? You can see there are the 4 number of the zeros, and what are the total number of the poles? Poles are my 5. So the answer of this problem is 4 minus 5. The answer is minus 1 is the correct answer of this problem. And you can see that this 4 is representing as the number of the zeros, and this 5 is representing as the number of the pole for this particular example in which I have considered these dots. Now this concept, whatever the concept they have used, this concept is known as the argument principle. Fine. Now recall that what are the zeros, because we need the number of the zeros, we need the number of the zeros, we need the number of the poles. So let me quickly recall you the concept of the zeros and the pole. For any function f of z, if I say the point z is equal to z naught is the zero of order m, or f of z is a pole of with multiplicity m, then what does the meaning of the order? That means you can write f of z is in terms of z minus z0 of order m, so you can write as the power m multiply with the sum function phi. Similarly for the pole, because as we have discussed in our last lectures related to the pole, limit point of the pole, we can define the pole. I can use as another function psi divided by psi minus psi naught raised to power m, where this phi function is my analytic, this psi function is also my analytic, and the value of the psi at the given point z naught is my non-zero. Similarly for this case, the value of the psi at the given point of the z naught is my non-zero. That's the definition of the zeros and the pole with the multiplicity m. Now to understand this concept, that is how you can find the integrations, you must know what is the concept of the zeros and the pole. So how you can evaluate these integrations. So for that we will discuss the concept of the argument principle in this lecture, which is basically the difference between the number of the zeros and the pole of the meromorphic functions. I hope all of you know what is the meaning of the meromorphic functions. If not, let me recall you. A function is said to be the meromorphic function if the function has no singularities other than pole in the finite complex plane. So based on this argument principle, we can define this integration. So what is the statement of the argument principle? If f of z is my analytic inside and on the closed simple closed curve C except at the number of the poles, then we can define this integration as n minus p, where n is a number of the zeros, p is a number of the pole inside the circle C. Fine. The proof is a very simple. So before watching the proof, I hope you can like and comment on this video as well. If you are new to my YouTube video, you can subscribe my YouTube channel as well. Now what is given to you? You can see they are talking about the number of the poles, they are talking about the simple closed curve and the number of the zeros and the pole. So let's see, C is my closed simple contour and I consider Z1, I consider Z2, I consider Z3 and I consider Zn are the number of the zeros. Zi's are my number of the zeros with the multiplicity alpha 1, alpha 2, alpha n. That means Z1 having the multiplicity alpha 1, Z2 is the zeros having the multiplicity alpha 2 and so on. Multiplicity you can also say in this case is the order alpha 1, alpha 2 and alpha n. Similarly, I can taken as a W1, W2 and the Wm are the number of the poles. Fine. Then we can define the circle corresponding to the each zeros. These are my zeros. I can define the circles. Let's say circle is my C1, this is C2 and this is my Cn. And I can define the circle corresponding to each pole as well. So I can call as the circle gamma 1, this is the circle gamma 2, this is the circle gamma m, or this is the circle gamma m, this is my circle gamma 1 based on the W1. Each of these circle is my radius rho and we can define these circles which are my disjoints. Fine. We can define the disjoint circles. Each of the radius, you can define the radius as say rho. So draw the disjoint circles, Ci's and the gamma I corresponding to the zeros and the pole. Then by using the Cauchy integral, we can find the integration is, that is sum of all those circles or the integral about the circles C1, C2 and Cn plus number of all the circles corresponding to the pole. So this is corresponding to my zeros and this component is corresponding to my pole. So our target is to evaluate these two components. This is your target. Now remember again, you need to recall the definition of the zeros and the pole. This is the definition of the zeros at the point zk, and f of z has a pole of the wj with the multiplicity beta j. We can define as a power is beta j, power is alpha j. So let's start with the first zeros. That means we are talking about the circle C1, circle C2 and the circle Cn. That means our target is to evaluate the values of the Ck f dash over f. Now we know the value of the f. So can you find the value of the f dash? So from the equation number 1, can you find the value of the f dash with respect to z? So I can differentiate them. Z minus zk alpha k minus 1 of phi z plus z minus zk raised to power alpha k of phi dash z divided by z minus zk raised to power alpha k of phi z. Now you can separate them. If you make a separate, this value will be alpha k over z minus zk plus if you separate them, it will be phi dash over phi of z. Fine. Now I can multiply with the 1 over 2 pi iota integrations f dash over f over the circle ck. So this will be integration on the both side over the circle ck. Now clearly say phi is my analytic. Fine. Phi is my analytic. This implies phi dash is also analytic, because we already proved that the derivative of the analytic function is my analytic. you can see in this lecture the derivative of the analytic function is also analytic. Once you know the phi is analytic, phi dash is analytic, what does it implies? Phi dash over phi is my analytic. And once we know, once the function is analytic, then the integration is my 0 by using the Cauchy theorem. Fine. So this integration is my 0. Now how you can evaluate this component? By using the again the Cauchy integral formula. This will be alpha k into 2 pi iota. Fine. So that is alpha k into 2 pi iota. So the answer is alpha k. Similarly, we can define the same thing for the number of the poles. I can calculate the value of the f dash. So what is the value of the f dash? It will be psi dash of the z divided by z minus wj of beta j plus I can write this number is psi of z z minus wj of minus beta j. So it will be minus beta j z minus wj minus beta j minus 1 into psi of z divided by f of z. Fine. Now you can again separate them. So it will be minus beta j, psi will be cancelled out, z minus w j plus if you cancel out it will be psi dash over psi. Again psi is my analytic, that means psi is my analytic, psi dash is also analytic. Fine. That means psi dash over psi is again analytic function. So I can multiply 1 over 2 pi iota over the circle gamma j because they are indexing with the j. Again this component will be my 0 by using the Cauchy theorem, and this component will be my 2 pi iota by using Cauchy integral formula. Fine. So this answer will be minus beta j 2 pi iota. So I can substitute both the values in the given equation. The answer of this is my alpha k. Value of this is my beta j. As you can see, the value of 1 over 2 pi iota is my beta j. So what does the meaning of the alpha k? If you open them, it will be alpha 1, alpha 2 plus alpha n minus beta 1, beta 2, beta m. And you know what are the alpha i's? These are the zeros multiplicity. That means the sum of the zeros. So I can say the number of the zeros, where p is the number of the poles. These are my poles of the multiplicity. So I can say n minus p is the required proof of the result. And you can see it's a very simple proof. You just need to evaluate the derivatives and then integrations. Okay, the first corollary is if you have the simple closed curve, then I can also write this function is 2 pi iota. If I take integration, it is f of z over the closed curve C. Is it fine? Now in the complex analysis, you always know how you can write this log of z. It is log of z plus iota argument of the z. This is the formula for the log of z. So I can write this function is 1 over 2 pi iota. This is log of the absolute value of the fz plus iota argument value of the f of z. Now the value of the, I can write also this part is 1 over 2 pi iota. This is log of f of z over the curve C plus iota argument of the fz over the curve C. Now this value will be my 0. Why? Because because the value of the log of fz retains to the original value when z moves along the curve C. So this value will be my 0, and the answer of this remaining part will be iota will be cancelled out. It is 1 over 2 pi argument of the fz. Second corollary is, so therefore you can say the left hand side this number by the argument principle is n minus p. So therefore I can say the n minus p is 1 over 2 pi. This is a variation in the argument once the z move over the curve. and I can also say this number is my 1 over 2 pi iota f dash over f. Second corollary is whenever the function is analytic, then we all know there is no pole. Fine. Whenever a function is analytic, there is no pole. That means p will be 0. Once the p will be 0, then this equation becomes 1 over 2 pi iota f dash over f and so on. I hope you can like and comment on this video. Now there is one more concept which is a very useful for the CSR net and the GATE examinations. Once you are the student of the GATE and the net examination, let me know in the comment box. I can tell you the where you can find my other videos related to the complex analysis. Now the concept of the generalized argument principle is if I consider the f is my analytic, g is also the analytic functions such that your target is to find the value of 1 over 2 pi iota f dash over f multiply with the f g of z. Then the answer is again the number of the poles minus number of the zeros minus number of pole, but instead of that it must be as a gk into gj. Fine, where g is any of the analytic functions and n and p are my number of the zeros and the number of the pole. Clearly say what will happen if you consider that any of the analytic function is my constant 1. Then if you consider that g of z is my 1, then the generalized argument principle is reduced to the simple argument principle. Now let's see how you can solve the problem with the help of numerical examples. Clearly say for the given function f you are unable to find the f dash. It is not easy for you that you can find the derivative of the functions, but whenever you have f dash over f, then you can apply the argument principle. Fine. So your target is to find the number of the zeros and number of the poles of the given region. So firstly draw the region. Z is equal to 3, that's a circle of radius 3. This is my minus 3. This is my curve of the given circle. Fine. Then by using the argument principle, our target is to find the value of the n and the value of the p. So let's start with the firstly to find n. What is the meaning of the n? We have to find the zeros of the given function f. How you can find the zeros? Zeros means we can take the numerator part as a 0. Can you find the value of the z? It is a z square plus 1 is 0. That means z is my plus minus iota of multiplicity. Can you find the multiplicity of this? Because of the power 2, it has the multiplicity 2. Now look at that where the value of the z plus minus iota lies. You can see what is the value of the z plus minus iota, that is a 1. 1 is less than of the 3, so it lies inside the circle. So both these zeros lies inside the circle. Therefore number of the zeros are, that means what are the roots? Iota is a multiplicity 2 minus iota minus iota. So the multiplicity is 2 plus 2, that is number of the zeros are my 4. Fine. So this is the way you can calculate the n. Now how you can p? P means that is the pole. You can find the denominator as a 0. Once you can substitute denominator as a 0, can you find the value of the z? This number is my 0. This implies z plus 1, z plus 2 is equal to 0. This implies z is equal to minus 1, minus 2 of multiplicity. Can you find the multiplicity of this? Look at the power. The power is my 3. So therefore it has a multiplicity 3. Fine. Now look at that whether the minus 1 lies. Where is the minus 1? Here. Minus 2. This number, because this part is my minus of 3 and both the values lies inside the circle z is equal to 3. So therefore the multiplicity, that is the number of the poles, are my 3 plus 3, because minus 1 is occurring at the multiplicity 3, minus 2 is also as the multiplicity 3. So I can substitute the value. This is 4 minus 6. So hence the answer will be, because your target is to calculate only as the integrations, I can multiply the 1 by 2 pi iota on the both side. Answer is minus 4 pi iota is the correct answer. So remember student, your target is only to calculate the number of the poles, number of the zeros. Always remember, you can watch about my previous lectures related to the singularities, limit point, to know more about how you can find the zeros and the pole of the given functions. This is the one example I have discussed in this lecture. We will cover the 15 plus examples, more examples on the argument principle in our next lecture. Till then, you can watch these videos, share this video with your friends, and don't forget to like and comment on the videos. Hope you can subscribe my YouTube channel as well. Best of luck, students. Happy learning.